Perhaps we can make a soft start, coming back to this slide. So this is certainly true for discrete distributions. So just to motivate again the Kaplan-Meier estimator, what we do is to try to estimate this probability at each event time, each jump time. And see that 1 minus is okay. And then how do we estimate this? Right, t greater than t is equal to uj, given that t is greater than or equal to uj, that will be written there. So we estimate that here by saying that at this time, ti, there are so many that could fail, and one of them failed. So the probability of failing is 1 divided by this number. And then we do that at each of the observed jumps, which are the failure times ti. We will see later today that if there are ties, there could be more than one that fails. Theoretically, since we look at continuous time, everything continuous, we so far have this one there, but if you have data where there are ties, where there are more than one that failed at this time, then that essentially should be written up there. The D will be called di, the number that failed divided by x. But the idea is to estimate these values. So then we were here. Duhamel's Duhamel come here, Duhamel's equation. And we agreed that this is a martingale. So here is where we stopped. Duhamel's equation. And since this is a martingale, we know that the expected value is 0. So the expected value of this must be 1. And that gives us approximately expected value equal to what we want for the S hat. And then we use, and here there was that where there was a printing error. That was then of course the same S here because it's this one. That then is approximately 1 or converges to 1. So by putting this equal to 1, we obtain here the right hand side just integral of the d thing, and that is the integral of dx is the same as x of t, for example. So this is this function evaluated at t. And we are thinking asymptotically now, so the star is not there any longer. We know that there are lots of units at the risk. That's what we assume then asymptotically when t, when n converges. So remember that there's never t that has a unit in these things. It's t is just the coming up to some tau. I have used that number, I think, in some places in the book. They say that we observe up to some time tau. It could be different from the different units too. So we will see that later when that comes in. But it is n that tends to infinity here. So this gives us this nice expression, and that's what we will continue using. And of course, that's from the elementary courses in statistics. We know that the variance of S hat of t will then be this squared times the variance of this, because this is only stochastic thing up here. And the variance of A hat we have estimated to be this thing. That's the estimate for variance. So then we estimate by just multiplying by S hat of t squared. So that's what comes out of this theory and this approximation. Asymptotically, this will be okay. Then there is an old formula, Green's formula. I have not that from 1924. That was before Kaplan-Meier estimator was invented. So I haven't checked what exactly Greenwood looked at, but there is this modification where we subtract 1 here. So almost the same asymptotically. But that's the one that is classically used as the variance of the Kaplan-Meier estimator. So then, when we have estimates for variance, we can find confidence intervals, and they call it confidence limits for SOT. Means that that is pointwise confidence intervals. So at each point t, one wants a confidence interval. We did that for Kaplan-Meier last week. So here's we use this estimator now, for example. And so-called standard interval is then S hat of t plus minus, this is usually 1.96 if you have 95%. But it could of course be other values. Then by the variance estimator, which was S of t squared times the variance, then we have to estimate S hat there, so it comes this and this. That comes from this here. So S hat of t times this. And then there is something that you will see in an exercise for next week, because we have an exercise for this week where we do something like that on the Nelson norm estimator. We will also be able to do it on this estimator. So this is an alternative estimate. And the advantage of this is that it never gets negative, for example. This could be negative if we subtract something from this, and we know that S of t is always positive. So this is, now you saw already the test data that I called them, the Kaplan-Meier estimate earlier. Here is then with these confidence limits, 95% confidence limits. Left we have the standard ones with plus minus the same thing. You see that plus minus the same thing here, for example. And here we have this log-log transform, which is see, much lower here and not that. It's a lower on both sides. So I think asymptotically, in the long run, this will give better results, but I'm not quite sure. But both are based on, we will have that in the lecture or in the exercise for today. They are based on that this is asymptotically normal, but if I take the log of it, or the log minus log of it, then I also get something that is asymptotically normal. Everything is asymptotically normal. So, so that's the idea here. And there is an exercise for next time where you are supposed to verify this interval. But that's how it is, how it looks. And this is, no, I do not have another figure here for this Kaplan-Meier confidence intervals, but there are, in the book, there are more like this.
What is it in that formula that gives that asymmetry? This is plus or minus.
What?
In the previous slide.
This one? Yeah, in the previous slide.
Yeah, what is it here that gives, so when you have 95% confidence interval on the log-log transform, that you get a different,
yeah.
that is no longer symmetrical?
It's plus minus up in the exponent here. And that's why it's not plus minus in the
Does that make it more difficult to interpret? I understand that if you can't get zero, that's the advantage.
Yeah, but if you see the derivation of it, it's not that difficult to interpret even. So it's our interpretation is is more or less that if there is an underlying SRT or an underlying distribution that gave us these data, then that theory might even have that might have had any SRT in this interval. So with these few data, we do not know exactly what the underlying distribution was.
I know, but what I meant was comparing it to the log-log transform.
Yeah.
That's what I meant.
Yeah. I don't know.
In what circumstances that would be more useful? This is what I'm asking.
No, I think that would be just empirically. We will see in practice. We could do some simulations, because with simulations we could find out if we simulated such curves from a distribution, we know the underlying distribution, then we know for each curve that we have here, we know whether, or for each set of confidence limits, we know whether the true curve is inside there. So then we could say, is it inside there with probability 95%, or, but this is pointwise, so we would have to do it in each point. So in this point, 80, we could then see whether these limits will be okay in 95% of the cases, or this will be better. So that's how one does simulation studies. And the research papers in statistics are full of these things. People come up with, this is a new confidence interval, and then they have to show coverage. Is it really 95%? So maybe that's more close to what you're asking. But then they do simulation studies where they simulate data from such a distribution, giving approximately something like this, for example. Now comes some little digression, because there come nicer things in the end here, other things in the end. Suppose that we have ties. So that means that at some event Tj, event time Tj, we have more than one observation. And then we have discrete data. Some times we have, for example, days. So the times Ti are measured in days, and we have 3 days, 5 days. Then of course there could be 2 in that has 3 days. So the question is, what do we do? And that is discussed in the book, chapter 313. Since sometimes I write this so that you can find the book. Suppose that we have time axis here, and here is my Tj, and then we have dj failure C. And now is failures not the sensor rings in between this. This is just the ones that fail there. So how can we deal with this? And there are 2 conceptually different approaches that the book describes. First is that in practice it is continuous time. So if we have more than one here, essentially they come like this, but one day, you say that is one day, and the time limit that we use is this one, or the registration is this one, then they could have come a minute, one of them a minute before the other, for example. So then in the formula, which is this 1 over Tj, then of course we would have had 1 over y of Tj, I mean. Then we would have had, for the first one here, 1 over y, but then comes the next one, 1 over y minus 1. And then it's not a Tj there, but yeah, it's the same. It is correct. That's what I say here. So essentially, if we had registered this in order, then I would come with this, because there would be 1 and 1 less. So this is this sum. And for the variance, we would then have, instead of this, we would have this. So that's exactly what we would get if we artificially, when there were 3 here, if 3 were registered at 3, then we would say put them at 3.8, 3.0, 3.2 instead, and you calculate the estimator. Then there will be one less at risk. Here, all will be at risk, here one less, and here one less. And that's exactly what this formula says. But then number 2 here is that data are genuinely discrete, so that we have, in fact, a discrete situation which we also have described. Then we couldn't do this, and then one uses instead just to say this, because that I think that is consistent with what I had in this formula: 1 minus probability that t is equal to uj divided by probability that t is greater than or equal to uj. If I wanted to estimate those things, then if I had y of tj at risk and so many fail, then I would estimate this probability to be dj divided by this. And then there is an argument, I think they refer to some paper or a book, that for this one, I should say that this is essentially y of tj and here to the third. So it's essentially this. It's essentially dj divided by y of tj squared. But there is something it's better. I didn't check what why that is better. But that's how things are done. So yeah, this was for the Nelson-Ohm estimator. For the Kaplan-Meier estimator, you can read about this here. In the first case, one just replaced one. I think that's what I thought of here. That they used dj divided by tj instead of 1 divided by. And for the estimated variance, they use something like this approach. And in case 2, where they are genuinely discrete, I think that Green's formula is the one that is preferred. And this is the one where you put this small order. So this was just a digression, so that you know how to do it and how R does it. Now comes a more important thing. Here's theoretically written what is easy to say on a figure. If this is my Kaplan-Meier estimator, such as one. Something like this. No, something technical to draw it. And I want to find the median. Let's take that first, the median. What is the median? The median is the what is here called C 0.5. So I just call it M. It is the one that probability that T less than M is equal to the probability that T is greater than M. So that means that you could have an equality on one of them, but usually it's defined this way. So that means that usually that means that S of T is equal to 1/2. But then these are equal, then they have to be 1/2 each. So then this is S of T, that must be equal to 1/2. So what we do to estimate it is that we take the Kaplan-Meier estimator in height 0.5 and go down here, and that is the estimated median. And that is exactly what is on this slide. Now we have the so-called P fractile, P. Here, CP is then defined as F of equal to 1 minus p. So how could we estimate that? We estimate it by by considering the Kaplan-Meier curve, infimum of the t, so that S hat of t is less than or equal to 1 minus p. So let's see what that means. P is equal to 0.5. That is the median. Then what should we look at? Infimum of the t, so that S hat of t is less than or equal to 0.5. So S hat of t goes here, and it is above 0.5 until you come here. So for this point, I think it goes like this. It's a continuous, let me see, it's continuous from the right, like this. So I have to find out when is S hat of t less than or equal to 0.5. Not here, but here, in this interval. Okay, and then that's the solution. The infimum of those t. Yeah? So it is from here and out. And the infimum is then this point. But in practice, it is just to draw the curve until we get to the right step. So if you have a step function here, we just go to 0.5. And if we have a p, then we should go to 1 minus p. So if, for example, p is equal to 0.25, then we should go to 0.75. So this is 1 minus p equal to 0.25. Then we get this number. So this is then psi hat 0.25. This is psi hat 0.5. And if we want 1 minus p equal to 0.25, then we should go, for example, there, and we get the same thing. I guess you see the point. These are called the quartiles of the distributions. The 0.25, 0.5, 0.75. But here they define it in terms of then, or uses the S curve, so then it's 1 minus that comes in there. So we see that there is no point here where we have exactly equal to 0.5, because here it is slightly above, and in all of this interval it is above, and when we come down here it is below. So we have to take something in between there. So this is a unique way of doing it. But then there is another thing that comes in that says that we can do in confidence intervals using this thing too. So let's go back to the test data that we looked at. This is the test data with, I think this is plus minus the standard confidence intervals there. If we do this, to get a median, we have to go out here, and we get 110, this data. And then, if I have these confidence intervals, that were 95% point-wise confidence intervals for the curve, then the theory says, and you are in fact given the exercise to show that is, gives us correct 95% confidence intervals, is to follow the same curve, and then as we cut this lower confidence curve, then we get the lower limit, and as we get the upper one, we get the upper limit. But here there is no one because this curve stops here, because it stops at 130. So we never hit this one. So the confidence interval is not properly defined. It's got from 70 to something that is up here that we don't know. So we could say that with 95% probability we are at least bigger than 70. And this is the median. So I think that's not trivial that would give us a 95% confidence interval, because the 95% confidence interval are made up vertically here, we take for this point plus minus the same thing. And then here we go horizontally. So that's an interesting fact. And we will, I think we will first look at this example. That is years since first birth. And this is only for the group who lost the first child within 1 year. So this is one of the Kaplan-Meier curves that we looked at earlier. In the middle, and then we have made up 95% confidence intervals, as we said. I think here they say that it is obtained, let me see, log-log transform. Yeah, that doesn't matter so much, but these are the log-log transform. And you see here that they look like plus minus the same thing. And when we have much data, maybe that's not so big difference between the two kinds of confidence intervals. But here again, we can estimate the median time between first and second birth for these who lost their first child. So then we just go into the curve and we get this middle number of these three. And then we hit the lower bound here, so then that will be a lower bound for the median. And then we hit the upper bound there, so that will be an upper bound for the median. So we get 95% confidence interval by looking at this plot. And that's very nice.
Question. Why did you write this half t and the half?
That was because p was 0.5.
Yeah, you wrote this there, yes.
To
left,
yeah.
Yes.
Where? Here?
No, to the left. You said t as an power of a half. Below that, to the right now. To the right. There, yes.
Mm.
What is the half power?
Yeah, I mean, if that's the definition of the median. If the probability that t is less than m is the same as the probability that t is greater than m, then that probability must be 1/2.
Oh yeah, now I get it. Thank you.
That's if they are equal and together they are 1. If we have continuous case, then if we disregard the possibility of being equal to m. But I think also in the discrete case, this is a definition of a median. Have you seen it? Because then it's what is in the middle is a little problematic. You find some m that is maybe it's not unique in that case. But for the continuous case, it is I could have had it over there or there. Yeah. So that's not there. So that was the definition of the median. And we could define it with a S of t equal to 1/2. And all that goes into this general definition. But this looks then a little complicated, but it is because we want a unique value. So, and when the curve, I mean there are no place where this Kaplan-Meier estimate is exactly equal to 0.5, then we take this when it drops down there. So we hit there. And as we get infimum of all these numbers up here, then where we are below 0.5. I guess we might also take the supremum of the t for which it is bigger than 0.5.
But this estimator of the median is biased, right? Because you're always going just one direction. So you will always get, the estimator will always be like a little bit less.
Okay.
Right. For example, in your example there, I would say that it's more, it will make more sense to go up, but you're always going down.
Yeah, okay.
So, and if that's always the case, then it's biased, right? Or
Yeah, maybe, yeah. So you mean that if we, but would it be no different if I took the supremum there, all the way greater than or equal to? I'm not exactly what, but of course one could formulate or modify the Kaplan-Meier estimator to go in between it. So let's go 1/2 in between each of these. that is a more smooth curve than this step. How will the median be then? Then the median will be here. It will be smaller. Is that was your idea? Yeah. And that's something that, in fact, is done for non-sensor data. So that there are different estimators that take not exactly the middle, but there are some formulas for where to go there. Yeah. But this is very nice that we can get these estimates, and but of course it is better here where you have much data. Then there is not so big difference. But it's very good that we also can make this confidence intervals there.
That curve, that one, that looks like a log-log transform.
That's a log-log transform, and but still it looks like plus minus the same thing.
Yeah, but then when you calculate the 95% confidence interval for the median, then you have to transform back, or is it just a straight?
I think that is said in the exercise for next time. If that was your question, you can still use this. You can still use this confidence interval. It's a 95% confidence interval still. But I think they say at the bottom of that exercise that we did this for the plus minus or the standard interval, but you could also do it for the transform interval, if that was the question. But maybe that was not the question.
Because if you were to write this, that I have a median of 1.9 years with 95% confidence, you couldn't possibly write plus or minus so many years because they're different. Right? How would you state that?
Yeah, how you say this? Yeah, that must be.
That's what I struggle with.
Inverse of this curve. Yeah. If you want to write a formula for it,
or just explain it.
Yeah. That's. But maybe we could do that with the exercise for next week. Yeah, we have to explain it, of course. Yeah. If you explain it by the graph, then people would understand it at once. So that it But there are different, as I said, these confidence curves are so-called point-wise confidence curves. At each point, they are 95% confidence intervals for the one single parameter, which is SO4, for example, here. But there are also something in the theory where you say that you have this curve, and then all curves in here, so it's a 95% confidence interval for the curve, so that the probability that the true curve, is within here all the time, that is 95%. That is something else. And I guess, but there is theory for that, I guess also for this kind. So I would suspect that maybe they are a little wider, but then any curve within there is there with 95% or whatever we could say. That's a little different. This is point-wise confidence intervals. So the theoretically minded statistician would not say that was so interesting with point-wise, but they use these curves. Where the curves are according to 95%.
Now let's do one more other question about discrete versus continuous time. Because even though an event has happened at a discrete time, but we haven't measured the events at discrete time. We've just, okay, it happened. The measurement has been continuous time. But the event has happened at discrete time. So what is more significant here?
Well, that is the opposite of what we said. Then the event was happening in continuous time, and we observed it in discrete time. But now it happens in discrete time.
Right. Yeah. So let's say you're doing this study, right, and then you're going to count the number of people exactly every 3 years, right? Every 3 years you make a measurement. That's discrete time.
Yeah.
That's not what you're doing there. What you're doing there is you're observing all the time in continuous time.
Yeah.
But the event happens at a discrete time.
Yeah. what you say can be related to interval censoring, but maybe it's not. Suppose I go to the doctor exactly each year, once a year,
Right.
and then I get a disease here. Then that is not observed until I'm here. So that is called interval censoring. Then we do not know exactly. For example, I go to the doctor here, and he says that you have that disease. But I didn't have it there, so then I know that it is in this interval. That's called interval censoring. All you know about the time is that it's between 2 and 3. And you can make a theory for this, because you can make a likely function and such things.
And that would make sense for me to call that discrete time.
Yeah.
Whereas if you're going to the doctor every single day,
Yeah.
but the event happens there between 2 and 3, then isn't that continuous time?
Yes, this is continuous time. So there could be a continuous curve SLT, but I do not discover it until I'm here. So that's called interval censoring. I'm not sure if that's something that comes up in this course, but maybe that's at least related to what you asked about. Now we would like to use our data to estimate the expected value of t. And then we know the formula, and that is the one here. We, in fact, studied it in exercise 1.3. We're supposed to do that. Where we use the formula for expected value. So then, since I now have an estimator, Kaplan-Meier, for S, why not integrate it from 0 to infinity? And that would give me then an estimate of the expected value. But so it's something here is problematic with the censoring and the fact that the value table is fully estimated. So I think the main reason is that we, for example, here we stop here. We do not have more data here, or if maybe we could go to this. Here the last time we had something was 130, and that was a sensor observation. So the last estimate was here. That was the last failure, 110. After that it was a censoring. So we might then say that the Kaplan-Meier curve, which is if we estimate, or if we write the estimate as the sum, the probability, this product of the Ti less than or equal to T of 1 minus this, if you look at this for example, then if I put T is equal to infinity, or very, very big T, and use this formula, then of course I would just continue this curve out here. But there is something in the theory that then I would have, of course, none at risk. So maybe that curve wouldn't be the result. But you might think this is the last thing I know about this curve. So to integrate it from 0 to infinity depends on very much what should I do here. Should I stop here? Should I stop there? And we know, or it is reasonable to think that it will continue out here. So the area and the SRT there, I don't know anything about. So this is not a good idea, in fact, to try something like that. But in the book I say that instead estimate the so-called restricted mean, which is the expected, I call it the expected survival in 0t, which is this function. So I just restrict this integral to 0t, and that can be estimated then for t for which we have this Kaplan-Meier estimated. And that is also done in R. What Minitab does, that I have used a lot, is to, in fact, if we have this, and here, this is for example the last observed time. That it was in my test data. It was 130. That was a sensory. Then it integrates up to that point. So that means in this case, I will show you that afterwards, after 130. But we might also stop here and do whatever. But of course, this is more easily seen as a problem when we have little data. But I think in any case, the tail out here is difficult to estimate because at some place the Kaplan-Meier estimator stops. So here is how we can do this R mean in R. R stands for restricted mean. So PC was what we used earlier, and we then say that we want R mean equal to 130, for example, in these data, and then they say here 96.07, and I even have a standard error for it, and a confidence interval for it. But that median and confidence interval are the boundaries, so that I think that has nothing to do with this mean, of course. That is a median, and a confidence interval for the median, and that's what we saw earlier, that we had 110 was the median, and 70 was this lower confidence limit, and then there was no upper limit. So this is not available or not computable then. It's not Nelson. So restricted mean with upper limit 130 is this one.
What does the restricted mean in practice?
Yeah, I'm not sure. Let me see what it is here. The restricted mean is then to take the integral up to here, then 130 in this case, but we could take lower. Now they're saying that it is the expected lifetime below t. Isn't that what they say? You can try to think of it. But here, let me see this one.
Yeah.
I think this is something that I didn't show you. But this restricted mean, which is this mu t, is equal to the integral 0 to t s of u to u. If t is equal to infinity, then it's the mean. But you see that it is the integral from 0 to infinity of the function s of u times the indicator that u is less than or equal to t. U. That's if you multiply by the indicator, this function of u is 1 if u is less than or equal to t, and 0 otherwise. So it's the same as integrating up to t. So we see that it is the expected value. Yeah. And you could say that s of u is a probability that t is greater than u. And then it is, since this is I think it is the expected value of t times the indicator that t is less than or equal to t. That's what we estimate. The expected value of t times this. So how to interpret this? This is the lifetime, which is equal to t. If t is less than or equal to t, and 0 otherwise. So I don't know if it has a very good interpretation. So if you think of lifetime of some component, But this is the mathematics. But before the break now, I would like to show this slide, which is about how to do in R, and you can check. So everything that I have in R here, I ask you to do yourself. I show some results of it. So this is again is test data, and then we have summary is one thing, but the quantile, this is a new thing. If you want these quantiles, then I wrote quantile fit C, and the probabilities 0.25, 0.5, 0.75, corresponding to these three things. And then for the test data, it gave here the quantiles, 50, that was a median, 110. We didn't go through that on the figure, but if I went to 25, that means I start at 75 here. Then I would go to 65.8. And for 75, I would not get anything because the curve stops. Maybe we have time to look at it. And here a confidence interval for the same thing. And you remember the confidence interval that we looked at for the median was from 70 to nothing. That was this one. If we want a confidence interval for the 0.75, that means 25 quantile here. That is 65.8 estimate, and from 39.2 to 110. I think we can look at it. And there is nothing for the 75. So let's look at the curve again. Here, if we want 75 up here, then we are up here somewhere. No, 75 is up here somewhere. And we get here 65.8, which is one of the points here. I'm not exactly sure where we hit. And the confidence interval is from there to there. You remember that was 39 something, up to 110, which is exactly the same thing as this one, I think. And for 0.75, we have to go to 0.25 down here. And then we see that I think we pass under the curve, so we do not get anything at all. I think. So that's, and this is how we could do that in R. And this was how we could find the 96.07.
On the graph, what would that 96.7 mean? I think you tried to answer that.
Yeah, that was the question. What is the interpretation of that?
Yeah.
So it is a kind of a lower bound for the expected value. You know that the expected value is probably bigger than this one because it's expected value of t times the indicator that t is less than or equal to 130. So if you only look at, if you had a lot of complete observations from that distribution, and you took out the ones that were less than or equal to 130, then that's the average of this. So maybe that's, since we asked for this interpretation, you could interpret this as if you had a complete set of data, then you take out the ones that are less than or equal to this number t, and you take the average of those. That's
exactly.
That's what it is. So it's so that's what I think in the book that said it was the expected lifetime up to time 10.